Okay, so this is tutorial 7. This is tutorial 7 point set topology. This is basically this is corresponding course number, hopefully NSC 24 MA 57, and today is 10 September. So okay, whatever I have discussed till the last tutorial, that is assignment 5 basically, and assignment 5 all the problem except the last problem, I mean due to time reason. So now I will first discuss assignment 5 last problem, the problem number 12, and then I will discuss assignment 6 problem, and after that I will discuss some problems related to the week 7 content, which will help to solve the assignment section. I hope I will get the time today, because today. Okay, so let's start with assignment 7 problem. I don't know what this one. Not this one. Yeah, this is the problem. This is assignment. This is assignment 5, problem number 12. I think I'm correct. Just let me check once. Yeah, yeah, this is correct. So what is the question here? It is that let X be the set of all symmetric matrices in GL2R. GL2R means all invertible 2 by 2 matrices with both the eigenvalues belonging to the interval 0 to 2, open interval, with the subspace topology from M to R. M to R means here subspace topology of R to the power 4. Then whether X is connected or X is disconnected, that is the question. And in last few problems of that particular assignments, like problems number 11, problems number um, problems number assignment 5, problem number 11 is the same type of problem. Problem number 12 is the same type of problem. What is the basic fact we will use? That if a let X, Y are two topological space, are two topological space, F is a map from X to Y, then F is a continuous map. I am taking F is a continuous map. F is a continuous map. Then F maps path connected set to path connected set. Path connected. Sorry, F maps connected set to connected set. Path connected is also true, but yeah, it will map connected set to connected. Maps connected set to connected set, and compact set to compact set. Compact set. How this connected set thing is happen? Suppose f of x that is sitting inside y, where I have to prove that if x is connected, then this fx is also connected. If fx is not connected, then I can write fx is equals to u division union of v. That means there exist two open set u and v, such that u v intersection is empty, and this will satisfy this property. Now particularly f inverse u and f inverse v, they will also be open in x. Why they will open in x? Because f is continuous. So as f is continuous, f should map inverse. F should take a open set on the codomain to a open set in the domain. I mean, pre-image of every open set under F will be open. That is what. So these two are open, and these two are obviously disjoint. So and we can write X is equals to F inverse of U disjoint union of F inverse of V. So that will contradict to the fact that X is connected. So that's why X should, if X is a continuous function from a topological space X to a topological space Y, then X should always map a continuous X should always map a connected set to a connected set and a complex set and a compact set to a compact set. Compact set. Okay. So now if X is suppose X is connected, um, suppose X is connected. Good evening, Vivek. No problem. I just started 2-3 minutes ago. Suppose X is connected and F is surjective, then F of X is equals to Y, then Y is also connected. So this is the idea. On the base of this idea, we have solved problem number 10, 11 of the assignment 5, and on the same idea, I will prove the assignment problem number 12 also. Y is also connected. Similarly, if F is surjective and X is compact, then Y will also be compact. Okay, this is the general fact. This is general fact. Okay. Now let's come to the problem number 12. So what will that X be the set of all symmetric matrices and GL2 are with both the eigenvalues belonging to the interval 0 to 2. Okay. So now for this I have what is the idea? Idea is mainly I will consider we will construct. Let's first take this is the this set whatever this is written that let this is the set as X. Okay, all those symmetric matrices M2R such that A transpose equals to A symmetric matrices and eigenvalue of A belongs to the interval 0 to. This is not all GMLR, this will be GL2R, all invertible. Okay, this is the thing. Interval belongs to the interval 0 to. So this is the collection. So what I will try to do here basically, okay, let's take this is the X, okay, as it is written X. So I will try to construct a compact set Y. We will try to construct a compact set Y. We will try to construct a, let's say here connected set. Okay, we'll try to construct a connected set Y and a continuous function f from y to x which is surjective. So now if we are able to construct a continuous function f from y to x which is surjective and y is connected, that will imply that x is also connected. So this is the idea. So now we know what is x. So we have to find what is y and what is the function f. So we know SON which is equals to SO2 here, particularly not n, SO2 which is equals to all those matrix MNR such that A transpose A is equals to I2, that means orthogonal matrices, but SO2, so determinant of A should be class 1, positive. And we know, let's D02, this is the all those diagonal matrices, something like diagonal, something like I can write x1, x2. I mean this is the diagonal matrices with the main two diagonal element. This is something like x1, 0, 0, x2, such that this is belongs to R2. I can write this is as R2 or R2 I mean Mn R2. Anyway, I can write this is as Mn R2. M2R basically, yeah, M2R such that diagonal. This is one such that, but such that xi and x2. Xi and x2 should lie between 0 to 2. That means all those diagonal matrices whose eigenvalues are in the interval 0 to 2. That is what. Now note that SO2 is path connected. Actually, why this is connected? Because that is path connected. Is connected. How this is proved connected? If you recall that GL NR plus, this is connected proved, this is path connected proof, so this is connected, and on the base of this idea, it is proved that the same way, okay, the same way as SLNR as a is connected, as I mean, basically that is giving as a, if you recall, if I write first, what is the idea that f of LNR is connected, f of LNR plus is path connected, that means connected, then we will give a bijective map, we'll give a, sorry, surjective continuous map that is giving by A is equals to, suppose A11, A1n, in this way, A n1, A nn, suppose this was the matrix, so the map was A11 by determinant of A, that is non-zero because A is in GLNR. Similar n1 by determinant of A, and this is all other element are as it is. So this matrix will be in SLNR. Okay, so this is the way we can give a surjective. This map will be surjective and will be continuous. So this will be surjective continuous. This is path connected. So this SL to SLNR will be path connected. So this is the way it is proved that SLNR is path connected. Similarly, we will prove that. Similarly, we can prove that SON is path connected by giving the same idea. I mean, just giving the same map. First, give a map from ONR for which determinant is ONR plus. I mean, all those matrices determinant is positive. That is same, and that is same with SO2. Nothing special. Okay, so this will be path connected. Path connected. So SO2 is path connected, and D02, this is also path connected. Why do you see this is also connected? This is not D0 close interval, D02, that means open interval 2, that means all the 2 by 2 diagonal matrices with the main diagonal element is 2, main diagonal in between 0 to 2, right? This is connected. Why this is connected? We can write the, look at it, we can write this is as basically 0 to 2 square. I mean 0 to 2 cross 0 to 2. Right, I can take x1 from 0 to 2 any point, x2 from 0 to 2 any point. That means basically this is actually product topology of 0 to 2 interval 2 times. And as 0 to 2 is connected, so product topology will be connected. So this is connected. So that means SO2 cross D0 to 2 is connected. Connected. Now what is idea? What is the idea? So now we have to give a map. Let's take this is equals to y. So we have to give a map y to x. X is a set that this is a set that all those matrices for which A is symmetric, and all those GL2 are matrices, and symmetric, and eigenvalues of A should belongs to 0 to 2. Okay, now if I give a map F from any element of y will be something like A comma B, where B is coming from this diagonal and A is coming from this SO2. So this will be like this equals to F A transpose B A. Okay, then clearly determinant of, first of all, you can look at this A transpose B A whole transpose, this is equals to A transpose B transpose A. Now B is diagonal matrix, so this will be like this way. So that means this is symmetry. Okay, first of all I can give this is not MNR, I can write this is as an MNR. Now we will show that this image of F under this function whatever defined, that is contained in A X, that is what. So this is symmetry first, and as lambda is if and if and if and as, okay, and as lambda is an eigenvalue of B, this diagonal matrix, if and only lambda is an eigenvalue of A transpose B. You can check this one. I already discussed in last class also. So if lambda is an eigenvalue of B, then lambda will be eigenvalue of A to B. But B is coming from D0 to. So that means eigenvalue of B will be in between 0 to 2. So that means eigenvalue of A transpose B will be, so eigenvalue of A transpose B A belongs to the interval 0 to 2, right? So that means you can look at image of the F will satisfy all other conditions, and also they note that as this is the region we have taken now, as A is coming from SO2 and B is coming from D02, so none of them have determinant 0. So determinant of A transpose B A, that will also not only 0 but positive. Okay, non-zero. This is better. This is non-zero. Positive because the eigenvalue is 0 to 2. Eigenvalue in between 0 to 2. And product of eigenvalues is the determinant. This is basically moreover positive. So that means f of x, f of y, that is sitting inside, f of y sitting inside x. That means f from y to x is a continuous function. You can look at this is continuous function. Why this is continuous function? Because if you look at the function how it is defined, this is the function that f of a comma b is equals to a transpose b a. So this is something like polynomial. Okay, n by n polynomial, n by n polynomial going to an n by n polynomial, something like this, and so this will be continuous. Okay, first fact is continuous. So fact is continuous. Now to show F is surjective. How to show F is surjective? Let's take A, B, A matrix from X. Okay, so let's take M here, not A, because A is already using it. M, B, A matrix for M. That means M will be symmetric, first point. Second will be like eigen value of M belongs to 0 to 2 interval, right? Now, as M is a symmetric matrix, this fact gives that M is diagonalizable. So we can choose an orthogonal matrix note that why we are taking here SO2, I mean why we are taking SO2, O2 is not connected, okay, but SO2 is connected. So this is the fact. Okay, this is better to write in little highlight. Okay, let's why we are taking here SO2. We can even here even if I took here O2, still we will get the surjective map, but that will not give our result. Okay, so here fact is that SO2 is not connected. Sorry, O2 is not connected. O2 is not connected. SO2 is connected. So this is the fact. So that's why we are taking SO2. Actually, we want to prove that this is connected. So if M is a matrix which is symmetric and all the eigenvalues belongs to 0 to 2 interval, then M is diagonalizable. So we can choose in any which is an orthogonal we can orthogonal matrix A such that we can choose an orthogonal matrix A such that matrix A and an diagonal matrix and the diagonal matrix B with main diagonal entry should belong to the interval 0 to 2. This is the thing. The main diagonal entries of the because why this is happening. Okay, diagonalizable. If you look at if you try to recall the linear algebra and diagonalization, so there it is the very general fact that if a matrix is diagonalizable, then there should exist an matrix such that this will happen that AM is equals to sorry. B A transpose M A is equals to D. B. This is the diagonal matrix, and this diagonal matrix will contain eigenvalues of A. But A is eigenvalues of M, but M is taken in such a way that eigenvalues of M should lie in the interval 0 to 2. So that means eigenvalues of B should lie in the interval 0 to 2. So we can write A is equals to A transpose B A. But note that we can choose. Note that okay, if we are in complex spaces, then this A will not be a orthogonal matrix, right? then A can be a complex matrix, right? But as we are in real case, so A will be always orthogonal matrix. First fact is the, but we note that A is in orthogonal matrix, but we can choose, but we can choose A in such a way that A is belongs to SO2. Why this is happening? Okay, when you do the diagonalization, so there what is the A actually? A is the, basically if I replace eigenvector, suppose the matrix M has two eigenvector lambda 1, lambda 2, and corresponding to these two eigenvalue there is two eigenvector V1, V2. Then this A is nothing but V1 and V2. Replace V1, V2 in this way. Just this. V1 is some column vector, V2 is some column vector. This is the way A is in general given. So now suppose A is in such a way that A will be orthogonal, there is no problem. But if determinant of A is not 1, so whenever A transpose A is equals to identity, that means A is orthogonal. So determinant of A is either plus 1 or minus 1. But suppose it is plus 1, so we don't need to do anything. If it is minus 1, we will just change one vector V2 by minus of V2. Then determinant will change. Okay. So basically, what we can, I mean, in short, what I will write here: if A is in O2 and A is equals to V1, V2, and the determinant of A is equals to minus 1, then replace A by matrix V1, or we can add minus 1 any places, that doesn't matter, right? These V1, V2 are not a single element, they are 2 by 2, something like this way. These are V1 like this way, right? So this is the main point. Okay, so this is the point. So what we have proved here basically, what we have proved that there exists an A and B, which is A is in SO2 and B is in um, B with the eigenvector is in eigenvalue in 0 to 2. That means f of A comma B is equals to A. That means f is surjective. Then f should map connected set to connected set. As y is connected, f of y is equals to x, then x is also connected. So this completes the proof. If there is any doubt, please go ahead. Otherwise, I'll go to the assignment 6. X is connected. Okay, thank you. Assignment 6. First problem is, let's move to the next one. Okay. Yeah. I hope I'll try to. My plan today is to do some problem from the assignment. Do some thing for assignment 7. Okay, let's see what I can do. Okay, maybe connected. Yeah, this is the problem number. Yeah, this is the problem number 1 of assignment 6. I'll try to that as let Y be a proper dense subset of a Hausdorff space X. Then Y cannot be compact. Yeah, this is the first one is the correct option. Y be a proper dense subset of a Hausdorff space X. Okay, we know now. First is the fact or theorem, whatever you know. Let X tau X be a Hausdorff topological space. Hausdorff topological space. Then if Y subset of X, then if Y subset of X is compact, then if Y subset of X is compact, then Y is closed. Right? This is the thing already proved in class. If I take an Hausdorff topological space, and if there is in a subspace which is compact, then it is closed. Okay. and closed subspace of a compact matrix, compact topological space is again closed, but this is the Hausdorff, this is the special property of Hausdorff. If it is compact, then it should be closed. That is the special of Hausdorff space. Okay. So now on the fact of this, if let Y be an proper subspace of x comma tau x, that means Y is subspace of X, that is proper, so not equals, and dense, proper dense subspace. And this Y closure is equals to X, right? So if Y is compact, if Y is compact, by the above fact, we must have Y closure is equals to Y, because that is the Y is closed. That means we must have Y is closed. That means Y is closed means this is the thing that Y closure is equals to Y. But Y closure is equals to X because Y is dense in X and Y is something like proper subspace of X. So that is a contradiction. That means this is a contradiction. So Y can't be compact. So this is the theorem. So first option is correct. Y can't be compact. This is the first option. First option is correct. For second option, suppose if X is compact and Y is, if X is compact, then Y should be compact. Whether this is correct or not, that is false. Let's take X is compact, then Y is compact or not. Let's take X is equals to close interval 0, 1 is compact in subspace topology. Okay. Let's take Y equals to 0, 1 is not compact and proper dense subset of X is equals to 0, 1. So if X is compact, then Y should be compact. That is false. So B is not true. So B is not true. C, X can't be compact. That can be. Suppose for this example, this is the example. B, you can take C here then. This is the example. C is not true. Because here we can take X is equals to close interval 0, 1, Y equals to open interval 0, 1, then Y, X is compact. Y is a proper dense subspace. Okay, still there is no problem. So X cannot be compact. That is false. Now X and Y both are compact. That is also not needed. So D is also not true. So these three are will work for her. D is not true. Why? Because X and Y should be both compact. That is not necessarily needed, right? Because X here is also compact and Y is non-compact and Y is a dense subspace of Y is a dense proper dense subspace of X. Okay. So now go to the second problem. Does there exist a bijective continuous map? Yeah, this is very interesting problem. Does there exist a bijective continuous map F from S1 to close interval 0, 1? Yeah. The bijective continuous local this one or this one. Yeah. This is the problem number 2. Question is, does there exist a bijective continuous function F from S1 to 0, 1? Okay, let's here first recall a fact, a theorem, basically a theorem. This is very important theorem, very important theorem. Okay, if you even not understand this theorem, just read the statement and follow it. It will be very helpful, even in exam, I think. So theorem is that let X and Y are two topological space F from X to Y be a continuous bijective map. If X is Hausdorff, and x is compact and y is housed off. If x is compact, and y is housed off, then this F is homeomorphism. So basically homeomorphism means inverse is also continuous. So here what is given, this is continuous and bijective. So inverse is exist, but only need to prove that inverse is continuous. So for this, what we are assuming that x is compact, and second is that y is housed up. Both of them are needed. We can't drop one of them even. Okay, so they both of them are needed. So this is the fact. So question here is that does there exist a bijective continuous map F from S1 to so? So if there exists a bijective continuous map F from S1 means circle, okay, 0 1, then as S1 is compact, okay, and 0 1 is housed off, then F will be a homeomorphism. But claim is there does not exist any homeomorphism from S1 to 0 1. Why there will not be any homeomorphism? We know, okay, just let's first try to understand this is a pictorial, okay? So okay, let's write. This is the S1. Suppose this is the circle S1. This is the center, and this is X. Okay, and this is the interval. This is the interval 0 to 1. Okay. Now, suppose there is a bijection. There is a bijection here, right? So now there is a bijection means for every point in between 0 to 1, every point in between 0 to 1, there should exist, every point in between 0 to 1, there should exist a point on this circle, on this circle. So now in particular, for a point here, there should exist a, say, pre-image. This is the pre-image, suppose. Okay, this is the pre-image. Suppose this is a point P. So this is the pre-image, that is F inverse of P, right? Now, if we try to find a, if we given the function like S1 minus F inverse of P, right? So and restrict it. Basically, I am restricting it F inverse of P. So this is going to like 0 to P open interval and P to 1, this type of interval. Okay. So that means we will have this function is again bijective, and if it is continuous, so restriction on some space it will again be continuous. So this is continuous. Okay. Now, but if it is continuous, so it should map a connected set to a connected set. Now, if you look at this diagram of the circle, this circle, so what you will see after removing the point F inverse P from this circle will be something like this will be like something like just bending. This will be something like this way after removing a point. Okay, so that is connected, right? But this set after removing P will not be connected. But if there exists some homeomorphism, there exists. So we should have something like this, that this is connected, but its image is not connected, but it is continuous again. So that is the contradiction. So how this is happening? Let's take P a point from P a point, that is let's take P a point 0 less than 1, not 0 or 1, not end point. I am taking any point in between them. Then there exists a point F inverse of P belongs to S1 such that F of F inverse of P is equals to P. Okay. Then S1 minus F inverse of P, if I remove this point, is connected, moreover path connected. Just removing a point from the circle, that is connected, right? I can join 2 points by a path on this circle. And if restricted to S1 minus this F inverse of P, from S1 minus F inverse of P to 0 to this will be like close interval 0 to P union P to 1. So and if so it basically if there exists such, so basically I have to write here from here, if there exists any such homeomorphism, then for 0 to P we will have, then this is a bijective continuous function. Then as S1 minus after removing this single point FP is connected, moreover path connected, we should have we should have we should have f of s to the power 1 s power 1 minus f inverse of p, this is which is equals to 0 to p union p to 1 is path connected or connected, but that is a contradiction. That is a contradiction because this is not connected, right? It is a contradiction. So there does not exist any homeomorphism from S1 to close interval 0 or any close interval basically. So that means as there exists a bijective continuous map, so there does not exist. So that does not exist because if there exists that will be homeomorphism, but there can't exist any homeomorphism. Okay. So B is the correct. Does there exist? This was the question, right? B is the correct. Now question number 3. If is there any doubt, you can ask. Otherwise, I will automatically go. If there is any doubt, you just ask. Okay. Then I'll stop and try to address. Okay, question 3 is very stupid. I will not do. That is, there exists a sequence xn in S1 which has. Okay, yes, Vivek.
Sir, I had a question. Can there exist a continuous bijective function from open interval 0, 1 to compact interval 0, 1?
If sorry, just a minute. You are saying that if from open interval 0, 1 to close content, this is the thing. This is the thing, right?
Yes, sir. Can the function be continuous as well as bijective?
Does there exist a continuous bijective function? Right? This is obviously not. This is obviously not. Why this is not bijective? Okay, no, sorry. Does there exist a continuous bijective function f from open interval 0, 1 to close interval 0, 1, right?
Yes, sir. Right.
Uh, First of all, right hand side is housed up, that is okay, but left hand side is needed. I think that is correct. That is possible. I can draw. Mm, okay, this is bijective also, right? Does
Yes,
there
sir.
exist?
If it was not bijective, I could also draw it like.
Right. You can draw a repeated times type of things, right? And which
Yes,
is
sir. Yes,
doing
sir.
the.
But
So injectivity is the fact. Injectivity, if you remove injectivity, then we can draw whether
yes, sir.
injectivity is
The
doing something.
problem comes in touching 2 points, na 0 and 1.
Right. Does there exist a continuous bijective function from 0, 1, open interval 0, 1 to close interval 0, 1? Achha, 1 minute. Does there exist any problem related to this type of problem in the last assignment? I think not this type of. There will be some little difference. Does there exist a surjective continuous function? This is the same question asked. Surjective continuous function. So that will not be. That is the what you are saying. That's correct. So bijective continuous function. No, no, it will not actually. Why this will not? Yeah, this will not. I think just 1 minute. 1 minute. Uh, if it is continuous function, it will map an interval to an interval. That's correct. First thing. Ah. So for 2 point, this is continuous function. So it should have. Okay. Even I think. Okay, there should not exist. Why this there should not exist? I think you can look at this one. 0 point, there should exist a point f inverse 0 in between 0 to 1 open interval. Similarly, there should exist a point f inverse 1 in between 0 to 1 open interval. Right? And this point, suppose this is the point x and this is the point y. Okay? So without loss of generality, obviously x is not equals to y. There is no doubt. Right? X is not equals to y. So that means either x less than y or x greater than y. So without loss of generality, I can take x less than y. So that means f is mapping f of this interval is the full interval 0 to 1, right? So that means if the point x is in 0 to 1 interval, right? So x will be like 0 less than 1. So that means there should exist a point which is in between 0 and x, right? Those points will map somewhere else, right? This is not y. This is not y. Okay, so point is okay. Just let me. This is not exist. Why this is the answer is no. Why? This is very much clear. This is I don't need to go any much more analysis here. Basic fact is that okay. Let me clear. I think this is I will tell you. No problem. The problem is that suppose I will suppose if so clearly f inverse x is equals to f inverse 0. This is a point, and y is equals to f inverse of 1. This is a point in 0 to 1. This open interval it should be there, right? And as f is injective, or if it's a well-defined map, so and so that implies x is not equals to y. That is for sure, because if x equals to y, so f of x will be 0, f of y will be f of x will be 1 again. So that is contradiction. I mean, 1 point can't go two way. That is not even a function then. Okay, so this is clear. Now by intermediate value property, and x and y belongs to 0 1, right? So without loss of generality, I can so either x will be less than y or y will be less than x. Without loss of generality, I can take is x less than y. That means f is taking value at the point x 0 and taking value at the point y 1. So if you look at this way, suppose this is the function, this is the 0 1, and this is the right, y axis 0 1. So f is taking value 0, f is taking value 0 at the point x. Here it is taking value 0, and here it is taking value this is y, this is x, this is y. Here it is taking value 0, and here it is taking value 1. So this is y comma 1, and this is x comma 0. So that means it should take as it is so by this is the intermediate value property. I hope you have known this. X less than y, then by intermediate value value property of f should take every value from 0 to 1 in every value from 0 to 1 or close interval 0 to 1 in between x and y. So this is the not formal definition. Statement is something like this. Okay, the statement is that if f is a continuous function, then f should have intermediate value property. And what intermediate value property says that if take value 0 at the point x and takes value y 1 at the point y, so in between x and y it will take all the value. So that means in between x and y, so it should take all the values. Something will be like this way, something will be like this way, something will be like this way, or something this way. Whatever, that doesn't matter. It is bijective or doesn't matter. But the point in the left hand side and the right hand side, those point will also take some value, right? At some values. So that means that at this point, it will take some value from 0 to 1. So that will repeat with the point where it is taking 0 to 1 from x to y. So this will be like 2 point, I mean, this will not be injective anymore, right? So that means there exists 2 point 0 less than p1 less than x less than p2 less than y, such that f of p1 is equals to f of p2. That will be. So that means f is not injective. So that is a contradiction. Is it clear?
Yes, sir, got it. Thank you.
No. Okay, so question number 3, actually there is nothing special. Question number 3. Question number 3 says whether, question number 3 says, not question, this is assignment 6. Assignment 6. Question number 3 says there exists a sequence xn. Question 3, there exists, let me write it. There exists a sequence xn in S1 which has no convergent subsequence. The answer is true, or second one is false. So okay, let's see. So this is false is the correct option. True is there, because as S1 is compact. So compact metric space, not only compact metric space. What is the metric here? Metric basically metric space of R to the power n. Okay, S1 here, metric space of R square basically, yeah, right. So question theory, there is nothing. Question 4. Question 4, what question 4 says that the set of rational number is locally compact. This is very interesting. So let's take the question. Rational number is locally compact. So this is, answer is false. Why this is? That means x, why q is not locally compact. That is the thing we will prove. So what is the definition of locally compact that I should write? Definition: x tau x is called locally compact. Is called locally compact if for every point x belongs to capital X, there exists an open set U of U belongs to tau x. That is the definition of open set, such that x belongs to U and U closure is compact. So this is the definition. Okay. Now let's take a point 0 belongs to the rational number, right? This is the point. Okay. Then there should exist an open set U belongs to Q tau Q, such that 0 is belongs to U. Okay, this is when, if Q is locally compact, then as 0 is in Q, there should exist an open set U such that 0 belongs to U and U closure is compact. U closure in rational. Okay. Now as U is an open set, so there should exist an epsilon greater than 0 such that 0 belongs to minus epsilon to epsilon intersection Q, which is sitting inside U. This is the in general. This is very general. I think I don't need to repeat here. This is the there should exist in epsilon greater than 0. What is the in real? What is real in the definition? A point 0 is sitting inside an open set U in real analysis means that there should exist an epsilon greater than 0 such that 0 should sitting inside minus epsilon to epsilon that is sitting inside U. That is what mean. But if an open set in rational means U intersection Q, that is what. Open set in real and intersection rational, that is the open. I mean basically U is something like U dash intersection Q, right? So there should exist an epsilon greater than 0 such that minus epsilon to epsilon that is sitting inside U dash. So that means intersection Q should sitting inside this one, so that is equals to U. This is the main point. Okay, so this is the explanation. Okay, I can even write here. Now U is equals to some U dash intersection Q. U is open in R. 0 belongs to U. That means there exists U dash. That means there exists epsilon greater than 0 such that minus epsilon to epsilon that is sitting inside U dash and 0 is sitting inside. That implies 0 is sitting inside minus epsilon to minus epsilon intersection Q subset of U dash to intersection Q, which is equals to U. This is the definition. Okay, so there will be this point. Okay, so now I will take an irrational point. Here we are taking rational. Okay, that is, so now there exists a point C. Okay, I can do two way. That's first I will do this way. Then I will take an irrational number. Take an irrational number. Irrational number R in between 0 to epsilon. Okay, so that means R is not in minus epsilon to epsilon intersection Q. This is not here. R is not here because R is irrational, right? R is irrational. But by reanalysis, but there exists a sequence xn of rational number such that okay, there's existent rational number sequence of rational number sequence of rational numbers such that xn converges to R, and these xn are not only rational number, they are coming from 0 in intersection Q. That is possible. That is not a big deal. This is from real number. That every sequence, every real number can be approximated by a sequence of rational number. Every rational number can be approximated by a sequence of irrational number. That is what. So that is what. So here I have taken an irrational number and got a sequence xn which converges to R, and xn is coming from this rational sequence. Okay. Then xn is in between this 0 to epsilon intersection Q, which is actually sitting inside U, which is sitting inside U closure, right? But Q is a matrix space and U closure is a compact set in the matrix space Q and DQ. DQ is basically coming from the real matrix space. Okay, that means any sequence in U closure must have convergent subsequence. So xn should have a convergent subsequence in U closure. Note that U closure in rational. And when we say a xn should have a convergence or a sequence converges in a set, that means the limits also be of that set. That means R should be in U closure because U closure is compact and xn has a convergent subsequence. So that means if basically a sequence is converging, and if it has convergent subsequence, that means the subsequence also converges to the same limit one. It can't have that sequence converges somewhere, subsequence converges somewhere elsewhere. That can't happen. Okay. And also here limit will be same. Limit, either limit exists uniquely or does not exist. But here xn has a limit in U. I mean, basic point is that suppose I am taking a set 1 by n union 0, right? This sequence converges to 0. That means this sequence converges in the set 1 by n union 0. But if I remove the 0 point, then this sequence is not converged in the set of 1 by n. So, but if it converges, so it should converges to the 0. That is the what is the point I want to make. Okay. So that means if xn converges in U closure, so that should converge to R. So that means R is sitting inside R. That means R is rational because this is sitting inside Q, no? Because this is subset of Q. That is the what main point. R is rational. That is a contradiction. But this is a contradiction. If it is clear, then okay. If you have any doubt, please ask. So that means so 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 that means that means there for the point 0 we are not able to give this set U for which U is compact. That means rational is not locally compact. Is it clear? If there is any problem, please raise. Otherwise, I'll go ahead to the next problem. Okay, clear. Okay. Okay. Next problem is 5. Any subspace of a locally compact space. 5 is also very easy problem. That's why I'm not right here. Any subspace of locally compact space is locally compact. The answer is false. Take x is equals to real number and y is equals to rational number. Then y is subset of x. This is locally compact. Real number is locally compact and rational number is not locally compact. That is what we proved. Not locally compact. Okay. Now the problem number 6. But an open subset of a locally compact topological space is locally compact. This is very interesting. An open subset of a locally compact topological space is locally compact. So this is, I think, easier. Openness is the fact. Openness will be used somewhere. I think that is what I just want to say. Okay, so locally compact. How the space is locally compact? How the space? So there is also one more locally compactness for Hausdorff basically. For a Hausdorff space, for a Hausdorff space, fact. This is a fact, a theorem. For a Hausdorff space, X is locally compact if and only if for any pair X and W with W is an open set and X belongs to W, there exists an open set V such that X belongs to V subset of V closure subset of W and this V closure is compact. This is the also one generalization. So I will use this generalization to prove that a locally if X is locally compact Hausdorff space, then Y is also locally compact Hausdorff space. Let X be a locally compact Hausdorff space. Y be a subset, then Y is also housed up. Housed up is just coming to the subspace. There is nothing problem, no problem with that. Then Y is also housed up. Okay, Y is also housed up. We need to show that for every point. Let's take Y belongs to. So we need to show that for every open set, Y belongs to capital Y, and open set W in tau Y. This is the subspace topology. Subspace topology of Y induced from X tau X. Okay, that means the open set intersection basically. Okay, such that Y is sitting inside W, and obviously W is sitting inside Y. That is what. But note that let Y is open. Let Y is open. This is very crucial fact. So that's why this is giving. So Y is open. So now what I have to prove that now, okay, now as Y is open, as W is open in Y, so W is equals to some W dash intersection W. So where W dash is an open set in X tau X, right? That is the definition of open set. But as Y is open in X, W dash is open in X, that implies W dash intersection W, which is equals to W, is an open set. Now consider in X tau X. Consider this pair. Consider the pair in X tau X. I mean, now consider the pair XW in X tau X. I mean, main point is that suppose I want to prove that Y is locally compact. That means for this is Y basically. Yeah. I want to prove that Y tau Y is locally compact. That means for every point Y belongs to capital Y belongs to capital Y, and W is an open set in Y, W is an open set in tau Y. We want to prove that there should exist an open set V coming from V in tau Y such that X belongs to V, subset of V closure, subset of W, and V closure is compact. This is what I want to prove, right? But now what I have proved that this W is not only open set in X, Y, but that is also open set in X also, right? And the point Y is automatically, as Y is in capital Y, then Y is in X also. So now I will use the fact that X tau X is locally compact for the pair Y comma W. Okay, this is the what I fact I will use. So consider the pair in and as X is locally compact. Now X is locally compact. I am considering this Y comma W as a pair in Y. Pair means point is open set, such that point is contained in that open set. And this is open set now, this is open set in X. Okay. So this should be clear. Okay. Consider the pair YW in this. Okay. Locally compact. Then there exists a open set V dash in sitting inside that topology of X such that X belongs to V dash, which is subset of V dash bar, which is subset of W for all, sorry, and Y closure is compact, and V dash closure is compact, right? This is what. But W is already subset of Y, so that means we can take V dash is a open set. That means V dash is equals to basically V dash intersection Y. This is same because V dash is already sitting Y because that is sitting in Y, right? Okay, let me write clearly. But note that W is sitting inside Y. That means V dash is equals to V dash intersection Y. V dash is an open set in X. Now V dash intersection Y, that is in open set in Y, right? And as V dash bar is compact in X, then V dash bar is compact in Y. Try to do using finite subcover definition. If a set, basically my point is that if a set, suppose this is the topological space X, this is the topological space Y. Suppose this is the space V. This is the space V. So this is the space V. Okay. So this is the space Y. So now if V is compact in X, that means V has, every open cover has finite subcover. So now obviously in Y also will have finite subcover. I think this type of thing also proved in early, that if a set is compact in bigger space, it will be, and the set is contained in Y completely. That set is contained in Y completely. I mean every open cover of Y, every open cover of V closure, that is, and also V closure is sitting inside Y. That means every open cover of V dash closure, that is again an open cover in X, right? So that means there should exist finite subcover. So that finite subcover will be the finite subcover in the topology of Y dash. So that means that is compact. So that means we already get the point where whatever this is open set and V dash bar is compact. So that means there exists an open set V belongs to tau I V dash such that V dash bar is compact in Y tau I, and X belongs to V subset of V dash, which is subset of V dash bar, which is subset of W. That means Y is locally compact. So interesting fact is locally compact. So if I take a locally compact topological space, sorry, if I take a topological space that is compact, and if I take a closed subspace, okay, let me write it. Note: closed subspace of a compact space is compact. Open subspace of a locally compact open subspace of a locally compact space is locally compact. In mere view, this compactness, locally compact is something a similar type of things, right? But there is a huge difference actually. You can look at this difference, that closed subspace of a compact topological space is compact, but open subspace of a locally compact topological space is locally compact. Okay, I hope this is clear. Now I will do problem number uh, 6. I have done, right? X is locally compact. A open subset 6 is done. A housed up space. Okay. Next on 7 one. 7 is also clear. 7 will be like same on the base of same. 7 problem is that 7 problem is what is the housed up space on X is locally compact. Okay, that is that. Mm, not this one. Is it 7? Yeah, this is the 7. 7. What 7 is says that What 7 says that a housed up topological space X is homeomorphic to an open subspace of a compact housed up space if and only if X is locally compact. 7 is big? No, 7 is not big. 7 is the same, I think, same line. So note that Y is compact housed up space. Okay, what is the okay? This is true or false. Question is true or false. A housed up topological space X is homeomorphic to an open subspace of a compact housed up space if and only if X is locally compact. So let 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 X is homeomorphic to an open subspace of a compact Hausdorff space X dash, right? This is the compact Hausdorff space. Then clearly X is locally compact by problem 6. What problem 6 proves that open subset of a locally compact space is locally compact. Now here what it says that X is locally compact and X dash is locally compact and X is homeomorphic to a open subspace of the compact space. X is compact, that means X is locally compact. Sorry, I'll write clearly. I think that is what. As X dash is compact, as X dash is compact, X dash is locally compact. So any open subspace of X dash that will be locally compact, and any subspace which is homeomorphic to that open subspace that will be compact. So that means X is compact, right? Conversely, I think it is clear. If there is any doubt or confusion, you can ask. Otherwise, conversely, let X is locally compact, right? We need to show X is homeomorphic to an open subspace to an open subspace of a compact Hausdorff space. So what is the point that we have to take compact Hausdorff space as take this compact Hausdorff space as 1 point compact. If I can take this compact Hausdorff space as 1 point compactification of X. Okay, so suppose X is locally compact. Then 1 point compactification says that there exists a compact Hausdorff space in which, so 1 point compactification says that in which we can consider that is as a locally compact subspace. That is what? That means there exists 1 point compactification of X. There exists a unique. This is unique sense. There exists a unique compact plus Hausdorff topological space X cap such that X is contained in X dash as a open dense subset I from X to X cap such that I X cap minus IX is 1 point. 1 point. This is the 1 point compactification. Just to recall, I think you know very well. Okay, so that means you can take a 1 point compactification of that space, and then the main locally compact space will be that is open, right? There exists an open dense subspace. So that is open dense subspace as it is sitting inside as an open dense subspace. So I think this is clear now. So now question number 8. What question number is continuous image of locally compact space is locally compact. Continuous image of locally compact space is locally compact. This is problem number 8. What told the problem? Each continuous image of locally compact space is locally compact. That is not. you can look at the, here is a one point. Continuous image of a compact set is compact, but continuous image of a locally compact set is not locally compact. This is true. That means yes is not correct. Let's take Q. Q with discrete topology. Discrete topology means every singleton set is closed set, every singleton set is open set. Okay, that is the discrete topology. Q with discrete topology, I will write D, discrete topology, and Q with standard topology, and take this is the space X, and take Q with standard topology equals to D of S. That is standard topology means. This standard topology means this is that, I mean, as a subspace topology of real number. Topology of real number. This is the subspace topology of as real subspace topology of real number. Now, if I consider F is equals to identity map from X to Y, that is here discrete topology, here standard topology. Identity map then clearly F is bijective. F is bijective. That means F of X is equals to Y, right? And this is already we have seen in previous problem, not locally compact, right? And F is continuous. Why F is continuous? As in discrete topology, every subset is closed and every subset is open. Then for any open set U in Y with the discrete topology, with the standard topology ds, oh this is tau d, not d, this is tau d, this is tau s, d for discrete topology, s for standard topology. Okay, this is tau s for any open set u in tau s. F inverse of u is an open set in rational with the discrete topology, because inverse image is the set U itself and U is open because every subset is open in the discrete topology. So that is why the function is always continuous. Okay, so even if I whatever topology I can give, if I have a function f from, okay, but basically what I want to say here, basically suppose I have function from x to x, any topology, discrete topology, then always continuous. If I have discrete topology on left hand side, then this is always continuous. Okay, so that means but the fact is that rational number with discrete topology is locally compact. Why it is locally compact? For any rational number, x belongs to Q, we will get a set U that is actually singleton set X, such that X is sitting inside U and U closure is equals to, that is basically same because every set is closed. Every set is closed basically because every set is open. So that is why every set is closed. So this is closed. This is compact. So U closure is compact. Why this is compact? Because the set has finite subcover. Whatever the collection of open set which covers the singleton set X, there should exist a open set U which contains the point X. I will take only that one. Okay, so that's why it is finite compact. Finite subcover exists. Always finite subcover exists. Okay, so X so rational number with discrete topology is locally compact. Is locally compact. But f of rational number with discrete topology, which is equals to rational number with the this is not the so but the image is not actually image of a topological space is not something like this, but Q with the standard topology is not locally compact. So that's why this is this is not true. That is continuous image of a locally compact space is locally compact. The answer is no. So another fact is that note that a continuous function maps a compact set to a compact set. Maps compact set to a compact set or compact space basically. But a locally compact space, sorry, continuous function may not map a locally compact space to locally, but a continuous function may not map a locally compact space onto a locally compact space. Okay, this is the one more fact. Okay, next is question number 8. Question number 8, what question number 8 says that is continuous. Okay, sorry, I have done question number 8, I think. Yeah, question number 8. So next is question number 9. I think there is, okay, question is bigger, but his answer is very easy. Yeah, this is question number 9. X and Y are locally compact and housed of space, then X cross Y is locally compact or housed of. That is what property maintaining. If X and Y are what is called compact, then their product is again compact. So here is also locally compact thing is also maintaining. If X and Y are locally compact, then their product is again locally compact. This is what. Okay, if X and Y are housed of, then their product is housed of. I don't think there is anything to prove regarding that. If X and Y are housed of, then X cross Y is again housed of. Why? Let's take x1 comma y1 and x2 comma y2. That is 2 point in x cross y, right? So either x1 not is equals to x2 or y1 not is equals to y2. Two distinct point I'm taking. x1 y1 is not is equals to x2 y2. That means either x1 not equals to x2 or y1 not equals to y2. Without loss of generality, take x1 not is equals to x2. As x is housed of, there exists an open set u1, u2 belongs to tau x such that x1 belongs to u1, x2 belongs to u2, and u1 intersection u2 is not equals to empty, is disjoint. Then u1 cross y is the full set I'm taking right now. u1 cross y, u2 cross y are open set such that x1 comma y1 is sitting inside u1 cross y, x2 comma y2 is sitting inside u2 cross y, and u1 cross y open set in product topology such that u1 cross y intersection u2 cross y, this is empty. So that means x cross y is housed off. Okay. Now to prove locally compact. If x and y are locally compact, then I have to prove x cross y is locally compact. Now locally compact. Compactness of x cross y. So let's take a point x and y, a point in x cross y, and W be an open set tau of x cross y. This is product topology. Tau x cross y means product topology, okay? So that means W be an open set in tau x y. So that means and this is also not fact, and x comma y is sitting inside W. We need to find an open set V in tau of x cross y such that x and y is sitting inside V, which is subset of V closure, which is subset of W, and V closure is compact. This is what I want to prove. And this is the same thing proving that there exists a equivalent to proving that there exists an compact set K and an open set V such that x and y is sitting inside V, that is sitting inside K, that is sitting inside W. Why this is equivalent? Answer is as V closure subset of K closure, which is equals to K, because we are in Hausdorff, as x and y are Hausdorff. The basic fact is that what I want to show that suppose V is, I mean, if okay, let me clear it. What I want to show that I have to show that there exists an open set V such that x and y sitting inside V, that is sitting inside V closure, that is sitting inside W, and V closure is compact. That is what I need to prove. But I am saying this proving this fact is equivalent to proving that there exists a compact set K and an open set V such that xy belongs to V, and that is sitting inside K and that is sitting inside W. Why this is true? Because if V is subset of K, then V bar is subset of K bar. But K, X and Y are Hausdorff space. Then X cross Y is again Hausdorff space. Like X cross Y is, as X cross Y is Hausdorff space. So that means compact means closed is Hausdorff. That means compactness implies closed. Imply closedness. So that means, and this is sitting W because K is sitting inside W, so done, right? So I hope this is the thing. So that's why I'm saying that. So basically, I will prove that there exists an open set V and a compact set K such that x comma y is sitting inside. This is sitting inside V and that is sitting inside K. K is compact. This is the compact. Okay, this is the compact thing, and that is sitting inside W. This is what I will prove. Okay. So now x, okay, let's come back to the proof. So I'll prove this fact. I'll prove this fact. So now as x and y belongs to W, okay, so there should exist an open set, okay, then there exists a basic open set W1 belongs to tau y, W1 cross W2, where W1 is belongs to tau of x, W2 belongs to tau of y, such that x belongs to W1 cross W2, that is sitting inside W. That is the definition of basis. I am not doing anything rocket science. This is the thing. and this is x comma y. They're sitting inside here. This is, I mean, point by point proof I'm trying to do basically. So that means x belongs to W1 and y belongs to W2. Now, using the fact that x and y are compact, locally compact, not compact, are locally compact, there exists open set V1 belongs to tau of x, V2 belongs to tau of y, such that V1 closure, V2 closure are compact in x and y respectively, and x belongs to V1 which is subset of V1 bar which is subset of W1, and y belongs to V2 bar which is subset of V2 which is subset of V2 bar which is subset of W2. That means x comma y is sitting inside V1 cross V2 which is subset of V1 cross V2 cross which is sitting inside W1 cross W2 cross which is sitting inside W. But this is the K compact. So that means, and this is the set V, right? So x cross y is sitting inside an open set V that is sitting inside a compact set K that is sitting inside W, right? That implies that x cross y is locally compact. I hope this is clear. If there is any doubt, please ask. I think I have tried to solve this problem very detailed. Even if someone can read carefully. I mean, my handwriting is not that good that it will be readable after a few times later. Still, if it is readable, then you will understand, I think. Okay, this is question number 9. Next is question number 10. What question number 10 says that, okay, question number 10 is easy. Just two more questions and then I'll try to discuss at least one type of problem for the next assignment. Yeah, this is the problem number 10. If y equals to n belongs to z, n greater than 0, and x is equals to 1 by n, n belongs to z, n greater than 0, have subspace topology from R, x and y homeomorphic or not. Okay, let y and x have subspace topology, y and x have subspace topology as subset of real number. Then y and x will have a discrete topology. We will have discrete topology. Okay, discrete topology. So that means y with this subspace topology, that is discrete topology, and x with the subspace topology, that is discrete topology. Let us define a function f from x to y by f of x is collection of, okay, y to x, the same thing, y to x by f of n is equals to 1 by n is a bijective. Now, as y have discrete topology, f is continuous, and as x have discrete topology, then f inverse is also continuous. Because few minutes ago I have said that if the left hand side has discrete topology, then whatever the topology on the right hand side, function will be continuous. Okay, so here on both sides we have discrete topology, so and f is bijective, so f will be continuous, f inverse will be continuous. That means f is a homeomorphism. That means the option, yes, this is the correct. Now 11. 11 is if X bijective continuous map between locally compact Hausdorff space, then F is homeomorphism. The answer is false, but I have to prove. Just 1 minute. Not able to get. Yeah, this is the question. If from X to Y be a bijective continuous map between locally compact Hausdorff space, then F is homeomorphism. Okay, that I think we have discussed already. That is already discussed, I think. That is false. Where I have discussed, I think question number 2, I think we have discussed. Still, I can discuss a little bit. Does there exist a bijective continuous map between locally compact Hausdorff space? Okay, no, sorry. Ha, then F is homeomorphism. Okay, no, I think I have to write it little carefully. Locally compact. So let F be a bijective continuous map between locally compact Hausdorff space, then F is homomorphism. Bijective locally compact, need not be compact. Their function is F from S1 to 0, 1 close interval, right? So this is 0, 1 close interval is bijective continuous between locally compact Hausdorff space. That was not bijective, I think. Bijective, okay. There does not exist any bijective continuous map. That is what I proved. There does not exist any bijective continuous map of this form. But here it is saying that if there is bijective continuous map from X to Y, X and Y not mentioned, so I have to change. X and Y can't be this type of. Main point is that X and Y can't be S1 or 0 close interval because if there is then there can't exist any bijective continuous map like this, because that is what we proved. Okay, let's take whatever the hint it is given, that is I'll take. Let's take X is equals to 0, 1 closed open and Y is equals to S1. This is compact, that means locally compact. Okay, this is locally compact. Let the map F from 0, 1 0, 1 to S1 by F of t equals to e to the power 2 pi it. Check F is bijective. F is bijective. Clearly F is continuous. There is no doubt. Clearly F is exponential function is continuous. Okay, and bijective thing we have to prove. Check. That is well not a big deal, because surjectivity, any point in the S1 will be something like e to the power 2 pi it. So I will get the t from 0 to 1, right? And any point, if I take 2 point t1 equals to t1 and t2, then e to the power 2 pi I t1 is equals to e to the power 2 pi I t2. Then we have to check e to the power 2 pi I t1 minus t2 is equals to 1. Then t1 minus t2 needs to be 0. That is what my point. Okay. Either otherwise t1 and t2 will be distance apart 1. But then there is no 2 point in between 0 and 1. I mean, for example, if I take t1 is, for example, if I take t2 is equals to t1 plus 1, then this will be 1. I think I'm correct. Cos 2 pi plus I sin 2 pi. Cos 2 pi is 1 and I sin 2 pi is 0, right? This is correct. That means T2, only the different solution will be like T2 equals to T1. But that can't happen, because there is no T1, T2 in the closed interval, closed 0 to 1 open, such that T2 equals to T1 plus 1. That can't happen. So that is a contradiction. So that is the bijectivity check. So this is F is continuous, and F is continuous and bijective. Okay, now we got, and both of them are locally compact. Now question is whether F is, now claim is F is not homeomorphism. F is not homeomorphism, and that is very much clear, because if it is homeomorphism, if F is homeomorphism, then F inverse from S1 to close interval 0, 1 is a surjective continuous map, and as S1 is compact, we should have F inverse of S1, which is equals to close interval 0 to 1 open, is compact. But that is a contradiction. So we should not. So that is why this is there does not exist by so bijective continuous map between two locally compact Hausdorff space can't be. This is also one contradiction. Need not be homeomorphism. So that is what note one. If f from x to y be a bijective continuous map between two bijective continuous map between two topological space, between two compact Hausdorff space, between two compact Hausdorff space, then F is homeomorphism. Actually, we don't need that both of them should be compact and Hausdorff. We need this should be compact, this should be Hausdorff. This is compact, this is Hausdorff. These two facts. But when we have both of them are compact Hausdorff, we already have that one. But if f from x to y be a bijective continuous map between two locally compact Hausdorff space, locally compact Hausdorff space, then F need not be locally compact Hausdorff space, then F need not be what is called homeomorphism. Compact Hausdorff space, then F need not be homomorphism. This is the fact, need not be homomorphism. F is homomorphism. So there is lots of difference from compact and compactness and locally compactness situation. Okay, is there any doubt till now?
No, sir, no doubts.
Okay. So I will try to do some problem. Okay. I'll try to do some problem. I think basically there is two main factor in the next. I mean, week 7 content. There is week 7 content. So this is on week 7 content. Week 7 content. Basically, there is two main factor, main point in the week 7 content. First is that 1 point compactification, and second is quotient topology. Okay. So first let me try to what I want I can prove. I think 1 point compactification. Let's try to discuss 1 point compactification a little bit, and something something which will give, which will help to solve your problem. I think. Okay, 1 point compactification. Just a minute. I have to. It's better to take about 32. Uh, so so one point compactification is something like one point compactification. But it says that let tau x is topology, no need to write tau x actually, tau x be a locally compact topological space, be a locally compact topological space, but not compact. Okay, this is important fact. Not compact. Then there exists unique. This is also important. Unique. Unique in means homeomorphism. Okay, let's I'll write. Then there exists a unique. There exists a unique in homeomorphic sense unique. I mean, if there is two, then they are homeomorphic. That is what. There exists unique compact Hausdorff space X cap such that Hausdorff space with the property Hausdorff space X with the inclusion I from X to X cap such that first fact is X cap minus IX, that is actually a singleton set P naught. Second fact, I is continuous. Third fact, I is continuous. Third fact, I of X is open and dense, you can write open set in X cap. And fourth fact, I of X is dense in X cap. So what we got? Main point is that suppose I have a suppose I have a locally compact topological space. So with that topological space, I will add. The main point is that we will add one single point, and we'll define a new topology on that. Okay, and such that with that new topology, what will happen that the map I from X to X closure, this map, if I just give the normal inclusion map, I from X to X closure, then that map will be continuous, and the image of IX, that image of IX will be open and dense subset in X cap, and this if I remove the IX from the X cap, then I will get the point P naught. Okay, and then so this property will hold. Then X cap is called. Then note that main point is that X cap is compact and Hausdorff. That's why it is called compactification. And why it is one point? Because I'm after adding one point, we are getting this one. Okay. So what is the property? Then X cap is called one point compactification, which is unique up to homeomorphism, which is unique up to homeomorphism. Okay, that is up to homeomorphism. If there is two, then we should have homeomorphism between these two. Suppose we have X cap and X cap dash, then we will have a homeomorphism from X cap to X cap dash. That is what I mean. And the fact is that open set in X cap are of two type. If A is subset of X, let's take an open set in X cap. Whatever the topology we will define on X cap, that will be open set, collection of open set, right? So let's take U be open set in X cap such that U is actually sitting inside X. We don't need to, basically this is the X. I'm taking a point P naught. This is what. So U is sitting inside X, then U is open in X tau X. That means open sets, I mean basically in first case what I'm taking, that open subsets of X, they are open in x cap, and second is that if u is not completely contained in x, open set in x cap such that u is not sitting in x, that means p naught point is there, because that is the what makes difference, otherwise you will be sitting inside x. Then x cap minus u, note that you have p naught point, x cap have p naught point. Now x cap minus u don't have p naught point. This is a subset of x, is a compact subset of x, x tau x. Okay. So these are the total collection. First of all open sets. What are the open set? If I take your set, either that set will contain the point p naught or that set will not contain the point p naught. If that set contains the point p naught, so x cap minus u should be compact set, then that set will be in topological space. And if, sorry, in the topology of the x cap, and if that set is does not contain p naught, then that is already in a subset of x, and in that situation u should be open set in x tau. So these are the two collection. Okay. Now what I want to prove here is that basically 1-point compactification of a set. That is what I want to mainly, at least I want to prove 1-point compactification of a set. Right. That is what I want to prove basically. Suppose I want to prove 1-point compactification of, okay, we know that R to the power n is locally compact. R to the power n is locally compact. Then what is the 1-point compactification of 1-point compactification of R to the power n? The answer is S n minus, sorry, Sn, that is all. Yeah, this is all. Okay, Sn means that is basically S, which is sitting inside Rn plus 1, which is sitting inside x1, x2, xn plus 1, be sitting inside Rn plus 1, such that summation of xi square is equals to 1, I equals to 1 to n plus 1. Yeah, this is all. Now we know there exists a stereographic projection, phi from S of n minus north pole to the set Rn. Basically, if you look at the set, for example, for type 3 case, sorry, for n is equals to 2 situation, that is what I can draw at least. Okay, so suppose I have this is the sphere, and this is the point north, and we will consider the stereographic projection like this way. So this point is the map to this point. This is the what? This is the map phi. So every point on the Sn minus 1 will map to some point on the R to the power n. Here n is equals to 2 basically. Okay. So this is a projection is a homeomorphism. This is very interestingly homeomorphism. Okay. Is a homeomorphism. Now just a minute. That means then phi inverse from R to the power n to Sn minus n is a homeomorphism. That is no problem. Continuous and bijective, that's why it is happening. Now what I need to prove? We will prove that 1-point compactification is homeomorphic to Sn. This is what I will prove. This is what we will prove. Okay, so that's why we will recall a fact or theorem, you can say. Okay, the theorem, what the theorem is says that theorem we need to the theorem. Yeah, this is the theorem. Suppose let x be a x be a fact or theorem. Yeah, this is what. Let x be a locally compact topological space. Locally compact topological space such that locally compact topological space for which not such that for which x cap is one point compactification. One point, that means it will satisfy all those 3 4 properties. Then if T is any compact set, T is locally compact, how does extend to homomorphic curve? Yeah. T be a compact topological space containing containing x means there exists a map I from x to t such that I of x is open in t and I is continuous. This is the containing means. Okay, continuous map. Then there exists any. Okay, what point is that x is a locally compact topological space with the x cap its one point compactification and let t be a compact topological space containing x. Then there exists a continuous map. Continuous map. This is the existential proof. Continuous map from T to X cap, which is identity on X, which is identity on X, and sends all the element which is not in T of IX or T of X, T minus X to the point P naught, the extra point of the one point compactification. So that means basically the idea is that suppose I have X and this is the X cap, this is the one point compactification, and suppose this is the T. We have a inclusion. This inclusion is named as J. Suppose then there exists a map, unique map. This is unique map. I think there exists a unique map. There exists a unique map phi such that phi of Jx is equals to Ix for all x belongs to capital X. So here what are the element? Either element coming from x that at Jx or element which is not in Jx. Okay. So that means P of all the element y is equals to P naught for all y which is sitting inside T minus J of x. Okay. Now if we take, we should have, this is the theorem, so this is the theorem. Okay, now if we go back to our old thing, I want to prove that Sn is the one point compactification or Sn is homeomorphic to the one point compactification. Now if we take x cap as one point compactification of r to the power n, then as Sn is compact, okay, as Sn compact and r to the power n is equals to homeomorphic to Sn minus n point that is sitting inside Sn, these two are, this is small n, okay, Sn, this is sitting inside this one, this is sitting, Rn is sitting inside Sn. So that means there exists a unique continuous map phi. How it will exist? Rn to let, this is the one point compactification I is there. Now Sn is here. Okay. Now this is the point J. This is the J. Okay. So I can map J, I mean Rn to Sn. Basically, what is the main point is that if we remove a single point from Sn, that is full Rn. That point is N, capital N. This is the word. So there should exist a unique map phi such that phi is continuous and phi maps the point which is coming from R is equals to Ix for all x belongs to R to the power n. And if I take all x, I mean basically here will be f of gx, phi of gx. If I take full j of R to the power n, so Sn minus j of R to the power n, what is that point? That point is actually the north pole n, and this is the x close union of the point p naught. So that means phi will map all the point x to the whatever the image under here, and phi will map the north pole n to the p naught, right? Then phi is bijective. I think there is no problem. Bijective and continuous from s of n to x cap. This is housed of, and this is compact. So by the previous theorem that if I have a bijective continuous function from a Hausdorff space to compact space to Hausdorff space, then that will be homeomorphism. So phi is homeomorphism. So one point compactification of phi, one point compactification of R to the power n is homeomorphic to the R to the power n is homeomorphic to Sn. This is all. What this is what. Okay, just 1 minute. Yep. I think I will not continue. If you have any problem, you can ask. Otherwise, I'll stop here. Is this clear? Why, how this one-point compactification of the locally compact space R to the power n is Sn?
Yes, sir. It seems clear, but I think I will have to watch once again the recording.
Okay, okay. If you have any doubt, because the fact is that now we are in the point which will make little tricky, little tougher things. Okay, so if you have any question, you can ask. One more thing, there will be a class in Saturday in which we will discuss the questions of um, mainly questions of the week 7 content, questions of the week 7 assignment, and the and also there will be a tutorial at the Tuesday also. So I think 8th assignment will be very easy to you because there will be discussion, lots more discussion on the aspect. Okay, if there is no doubt, I think we can stop here, right?
Okay, sir. Good night.
Good night.